So, take, yeah, before the break, the approach of doing segmentation is to quad trees. It's not really looking at the image. Identify regions where they are. And the way we do it is we split the image in 4 pieces and check if there is some kind of, it could be that the variation is less than, say, 10 gray levels. It could be that standard deviation doesn't exceed you, or something like that. And in this case, we do it. Build. Then we do a next split. Okay. And we see that, okay, we still have regions that need to be split. Here we have some regions that don't need to be split anymore, and some regions that need to be split. Soon as there is an object in the region, we have to do it. And just number of splits. Closer we get to the edge, the finer small regions we get. And way that can be used to identify where we have objects. You can also do statistics for this region, gather into, in a way, from your object. Here's an example where I took a radiograph of a grasshopper and ran the quad tree segmentation. And in this case, it was the region maximum minus the region minimum should be less than threshold, and then it went on. The boundary, we have a little bit small now on this screen, but on your own screens you can probably magnify it better. And taking this one a step further, in the quad tree we still had squared pixels. With Supervised, you regions with some arbitrary shape that full criterion. And here are some examples from EPFL where they had where they show how it can be done. Here we have relatively large pixels, and then you can increase the pixel size and get more level of detail. And why we use these pixels, and also the quad reduce data size by doing this, because if you have regions very we can that also be used to you already initially oops. Sample now, we have 3 phases in the sample. Rock, clay, and pores. And just by thresholds on this image, it doesn't look very convincing. You have strange regions. You have even this large grain here is split in 2 pieces, which it probably shouldn't be. Also on the boundaries you have strange things. Uh, want to show you on this image, on this code, is this when you do IM show with segmented data, it's important that you use interpolation none, because this IM show, and if we run this sample now, if I take it out, no. Well, that didn't show up much different. Maybe you can see a little bit on this, on the, like it adds on more information which shouldn't even be there. Should have color map maybe. Let's see if we can do, maybe take, so in this one, look in particular here in this boundary, in this region. And now if I switch it to adding, yeah, this was a bad example. It happens too much at the same time. Okay, let's skip that. So anyway, now we do a super pixel implementation, and we can see here that we have a nice connected blocks. In particular, if we do the merging of the superpixels, then you can nicely see here that some of these regions come out very well. And here's the if you do pixel segmentation and if you do the superpixel segmentation. You have larger blobby blocks in the image, which is mostly of interest. You have to tweak it, but it's not. It's a good start. So this histogram-based thresholding, we did k-means clustering and then similar region. And that of this part. Supervised segmentation with that. Now we haven't told our segmentation exactly what we expect in the regions. And with supervised segmentation, that is changing now. Now we need a ground truth to tell our segmenter how to work with it. And there is again some reading material. This part touches it on machine learning. Wrong place, so I recommend you to maybe take put more attention on the ETH course on machine learning. Works, and there is some reading material around that. Again, we have a lot of here to modules to look at, and now we get a lot of things from scikit-learn, different classifiers, 3 classifiers here, and well, Neural network part comes later. Okay. But anyway, a lot from parts here too. What we can do is we have different methods here. Have classification, and we can do more or less just fitting method. And the important thing is that we have two steps now. One is, and the other one is predicting, where you take your data, try to. And in the classification case, we look now at, again, some blobs. In this case, we only have two. And we have these two groups. And in this case, now we have identified the group. And, oops, that wasn't. So, and then we have two. And training. So it's not k-means. K-means is neighborhood to tell B. So looking at these hikers, then when they walk in the forest, and they should tell which kind of forest they are in. If this one looks at only a single tree, it sees, okay, it's a pine forest. The next one, he looks maybe at that tree and say it's a birch forest. Or maybe he sees this one as closer, then it's still a pine forest. And this one, he clearly says, yeah, well, no matter what he looks at, how close they are, he tells this is a birch. Now, if we would increase the number of neighbors they are looking at, so for example, say we want 3, so that would be k equal to 3, then you can see this one still sees a pine forest. That one, now he sees a birch forest, rather. And this one sees clearly a birch forest. So of the number it's filling up a data space where you can combine, where you can compare your neighborhood with. And now at this example down here, I have plotted in 3 different points. In this case here, from here I can't tell if that one is closer than that one, but I think the yellow one, it would belong to the yellow one. But if you would add number of neighbors, you would maybe tend to go towards this, that one. But I think this one actually tends towards the yellow class. And then we have this other cross here, magenta cross. It's in the middle of the green. And no matter how many neighbors you take, it will be the green class. The last one, this orange point, yes, ambiguous region. If you take single neighbor, then you would say, okay, it's green. But if you take 3 neighbors, all of a sudden, then you are, what is it, purple? I don't know. Yeah. Then on the different neighbors you're working with, you can actually get different, and then you get different boundary bits. In this case with text, where we have different values, so that the values are the inputs and the classes are the words. And if we do this training, then we can see what happens, and we run it. We have testing. Number 200 is 3, and that would give me the class dog. If I would put myself maybe at 0. Then it would be I, and see which neighbor is the closest. And let's go back now to the blob data. We train it with these three classes. It's different classes, and here is really an outlier that could be confusing at some point if you have only one neighbor. So let's try the regression and do the training with this point data. So here we say we identify nearest neighbor classifier with one neighbor and see what happens. Do the fitting, and then we run it. And from you get and this to get this, you can here now with 4 neighbors, and then you have much clearer lines between two. Able to that crossover. We can a kind of a line curve where you can fit your input vectors to the ground truth and find some results from that. And the typical is just that you have a straight line that you can easily fit. It's not so fancy at all. But it's an example where you can do this fitting. Now a little bit more interesting is when we do when we have these blobs. Now we have the blobs and some group ID that we know, and we do again this linear regression on it. And from here we train. We have the x and y points, and we have the group ID as the output, and then we get some slope in x and y and some offset. Now, running the test data on this, you can see that we get actually a linear gradient, and it's easy actually to see in continuous image. And you can see that there is some kind of slope in the gradient here, and that is actually our cut line between the two classes. So we can set a threshold on this regression, and then we can tell if the value, which kind of value it is in the end. We're doing this kind of clustering is work with decision trees, and trees is say a structure in computer science. And confusing thing is that when you look at a tree in nature, it's usually growing upwards, but tree is actually having its central node in the top. It's growing. Drawn, but typically it has 2 branches and a decision. So if some criterion is fulfilled, then you go on one side, and if it's not, it goes on the other side. And with that, you can split in and making decisions about. Here we want to have an array, and we want to tell we have an odd or even number in our we train this tree, decision tree, of what you have. And oops, wrong way. Sorry. This we can also blob data. So we train this tree on the blob, and then it looks something like this. Data set. In the end, we have different categories. We have 3 end classes, and we see that we have 34 items in that category. Here we have 33. Here we have also 33 of that class. And it's now this segmentation is looking at feature vector x1, and here it's looking at feature vector x2, x0. And looking at this tree, in one case, it's doing this segmentation, and the other case, it's doing this segmentation. So it's actually segmenting along different axes. And the tree is always segmenting in angular blocks, not like in the k-nearest neighbor, which could give you some arbitrary shape. But this one is always giving you rectangular blocks, because you're only segmenting along different axes. It may not be the best solution only rely on a single tree, so why not go for using many and voting? And the principle is that you train of trees on different subset of the training data, and then from that you try to find out of all these trees. And let's make the data a little bit harder to understand. Big overlap here, and we want to look at 5 different trees. So we create 5 trees from this data, and we build them. And one of these trees, now you remember that it was also very hard to really distinguish, and that also reflects on the complexity of the tree. Of these trees, some arbitrary shape, and so on, and the combination of them gives the final result. Pipelines. Now we leave classifiers as such, and actually go over to, say, a text construct, which to create workflows. And in principle, a construct that where you can put in different processing modules and execute them, and you can simplify the coding in that sense, and also make it go. Have again blobs, and we want to analyze them. if we create a pipeline now, we now need to import this pipeline and some support stuff. Show pipe, that's just for doing the plotting, and robust scalar is that we add to this. And we create our very simple pipeline. So it's done by writing just pipeline and as the constructor. We can name it, so we call this module. And the syntax of it, you can see. But what it's doing is actually just looking for min-max. Now I don't know exactly it's in the default, but there are ways of just looking at min-max and divide it by the average value. No, subtract the average value and divide by min-max, or something like that. More or less. Quantiles, and then what you can see is that now we increase the pipeline a little bit, so we just add this quantile transformer to get some uniform distribution of the data, and again running the robust scalar. So processing steps is just adding pieces in a list here in the pipeline. So actually even configure your scripts on the fly, more or less. Say you want to add a step, your it can be a little bit more stiff in how you organize it. And running this, we can also create some polynomial features. Polynomial features is essentially just that you add, for example, the square. In this case, actually, I'm just adding the squared feature. And it looks a bit messy, the data. It needs some time to understand what it's actually doing in these dots. And now we want to use it. Now we've done some kind of scaling and reshaping, adding features, but we can actually also use it for data. So we load some data from the MNIST dataset. These are 8 by 8 pixel images, and we have examples of them. And when we load it, the first step is loading it, and then it's flat. It means that we just take and then we normalize it and see that all the pixel values, they are now centralized around the 0. And that was the operation. Actually run k-nearest neighbor classifier with a single neighbor. And the values you see here, or the colors, they should probably correspond to the actual labels. It's not so easy to see here, actually. So let's try fire. Add the run, and we see we had. Let's see. We have 7 zeros, we have 5 ones, and so on, and everything is fantastic. Other things like precision, recall, F1 scores, support, etc. Everything looks Really amazing. Fantastic classifier, isn't it? Oh, let's patent it and go to Google and sell it, get money. Let's see what happens if we try with some. We include which it has seen before, and we see that and the real value should be 9. And looking at the no, we don't see the confusion matrix here, but well, what happened is did the training and the testing with exactly the same data. And if you use k-nearest neighbor and using exactly the same data, you will get exactly an exact fit. And that is the problem. So what you need to do when you do training, split your data into training, validation to get your metrics, and then do some additional testing to really make sure that you're doing the right thing. And that we now in our algorithms and nice things. As alternative, we can also look at the idea now is to number, not a instead. And now first we take some images for labeling and for the training, and then we take a lot of images for the validation. This and we have a regression algorithm, and that should try to work with. You don't have to mess around. It shifts everything from one to the other. The problem is that you can't C-curve, you can't use the confusion matrix because you have real values. Instead, we're using the mean squared error or mean absolute error, and then you see the training, very nice fit. Just look at it. If you look at the validated data, you see that you have actually some outliers, and sometimes it doesn't perform that well. Then we can increase the number and see what happens, and hopefully it's improving, and here we can see what's actually, confusingly enough, didn't improve so much, so there is more confusion. So regressor is the best choice for this kind of data, so we need to look. Time is running away, but anyway, so here comes now of different ways of doing pixel classification, looking at the cells segmentation from electron microscope. And we can try different things. So I'm not of everybody. We can just see some things that we have first. We have our original image, and we have a mask image, and the translation on this data. And we split out some regions, actually splitting the image in 2 pieces. One that we use for the training, and one we use for the validation. Then we run our pipeline on this, and we can see that the work on the prediction mask doesn't. So this is a regression tree. Doesn't work pretty well. You can see that it's actually finding more or less every boundary, and also looking at the full prediction mask, it's not really convincing. So that was a bad choice. Then we can add the tree with some position information, see what happens then. It improves, yes, but in the in the validation data here, you see that it doesn't do a good job. So it's only working on the training. So that's also not a good idea. Then we make it more and more complicated. We do some random forests and see. And well, that wasn't either one. Yeah, so we add a lot of different features. Some of these they do good, less good. We can also add some kind of gradient information. See what that does to the image. This one actually turns out. We can also try working with the neighborhood. More or less training what happens if we include some neighborhood information. But also that didn't really provide. And yeah, also that is not a good idea. Nearest neighbor is another approach. Let's see. No, not good. So anyway, it's not an easy task for any of these approaches. And what we want, these pipelines, they're easy to configure. Just write this little list, and then you have your pipeline program variables, so it's easy also to read. But you have to be creative. It's classify methods, and some of them worked, some less good, and training data, so that was really bad ones. The segmentation is to do deep learning using a unit, and it's a convolutional network, meaning it has very, very many convolutions that is performed on the image, and these convolutions are combined some weights and some activation functions. And special thing with the unit, conclusion. A little unit. It looks not too bad. So we are using a package called TensorFlow and a sub-package called Keras, which makes it easy to actually produce these units, or actually any deep learning algorithm. And what you can see here, we have a lot of layers, and the layers, they have convolution 2D, and it's doing pooling. Pooling means then downscaling, and that's repeated a couple of times until we come to the bottom layer, and then we're doing upsampling again, and then we get the final activation output. And everything is then brought together into this model that we call small unit. That is summarized this, or we can also graphically look at it, and here you can see actually upside down. But you can see this U shape that we have input level, then we're doing downsampling, downsampling, upsampling, upsampling, and then we get the output. So this is the structure of a very simple convolutional network of the net. And now we need to train this data, this is quite demanding. So we take more training image. Seconds. You want to use graphic card acceleration, which I didn't manage to get running on computer. So I had to run on. But ideally, machine learning is done using a graphic card, which speeds up training quite radically. Then we have also a validation image, which is this purple or magenta shaped. And then we run, we have set it up, we have provided training data and validation data. And without starting any training, the predicted segmentation is not expected to be very good, and it is not. So it's more or less just a random guess. We have probabilities here, which are around 50%, so it's more or less random guess with some structure. This is expected. But that we actually which could have can change. In particular, what we do bad is that we use the same, more or less the same image for both training and validation, which you shouldn't. But now we are in time and data, so we have to settle all these limitations. There are a lot of stochastic gradient, the iterations, and then we check a couple of accuracy metrics to see how well the and then we see what first have some error curves here. Performance classification accuracy is actually working pretty well. The training data is, interestingly enough, less good than the validation. Should actually be better. It's maybe not fantastic. Small, yeah. And now we do some prediction tests, and we can see that we have very dark, so there is low probability, but still you can see some islands here which more or less correspond to what we want to look for. And then we do have some overfitting problem. It can be that we have so many parameters that we're tuning here, and easy to do. Optimizer and settings and see what that comes out with. And now it's actually does it's about the same accuracy, but it's not changing over the training period. And now what we get from this setup that we used now is actually improving a lot. It's a bit fuzzy maybe, but it's not too bad. It's actually following most of the shapes. This one is a bit strange maybe, what it does here. But in conditions is doing a decent work. We had a very little network. We didn't use the ideal training data. We should use data. And here I only so we look at different ways to automatize the segmentation. There are very many approaches. What you usually start with is some histogram-based method, and then you can go into clustering or supervised classifications. And all this testing can be supported by using, for example, pipelines. And important when you do the supervised segmentation that you really make sure that you have split training data and validation data and test data to not to avoid doing the mistake of thinking that you did a good job. But in the end, you just overfit on a single specific case. That's it for today.